I will do my best to finish CFT today. Okay, so sometimes we can guess what is the corresponding operator to a state. So in particular, if I have a state, there are no oscillators, but this state carries a non-trivial momentum, meaning that P mu activity is K mu 0, k. So if I look at this state and I ask, what is the corresponding operator that I need to insert? Well, so if I think about a wave function corresponding to a state carrying a momentum k, so for this state, if I make a translation, x mu goes to x mu plus k mu, right? So space-time translation. So we know how the wave function will transform, and so what will happen is that this state will get simply a phase, and so this phase is going to be equals e to the ika 0, k. So that's what we know. That's what we know from our quantum mechanics. And so we might try to guess. So can we come up with an operator which has exactly the same transformation properties under the space-time translations, and it's easy to make this guess. So it's e to the I k mu times mu. So this is the operator that has exactly the same transformation properties. Okay, good. So, so what I want to do now, I want to actually talk. So the discussion that we had before was a little bit heuristic, and I want to get a little bit more precise. And so we talk about relations between operators and states in path integral formula. So the first thing, what I promise you we will do, so you give me an operator that sits on the origin, and what we want to do, we want to construct a state, okay, corresponding to this. And so the way this is done is that we're going to construct a Schrodinger wave function corresponding to operator A. So this is the Schrodinger wave function corresponding to the operator A. Right? So this, I say wave function, you have to think of this as a wave functional. It will depend on the fields, right? So I'm going to put phi set b. So what I'm writing so far is general. So it's applicable to any CFT. You can ask the question, if you give me a state, what is the core? You have some local operator in there. You have some local operator in this theory. What is the corresponding Schrodinger wave functional? And so what you have to do, you have to evaluate. You have to evaluate the path integral, right? So. So here I have e to the minus s phi. So here I have a local operator a of 0, and so when I evaluate this path integral, I have to provide some boundary conditions, right? So I have to require. Well, so we can be a little bit more specific. So we can think that we're defining this Schrodinger wave functional, say at absolute value of z equals to 1, right? So so here what I have an integral. So d to z. So this is an integral of a unit disk. Right? So I integrate over all possible field configuration up to z equal 1. That's, if you wish, that's the time at which I define my Schrodinger wave functional. And so I integrate over all possible fields such that there is a boundary condition, right? So that phi on the unit disk on the unit circle equals to phi boundary. In other words, I evaluate a path integral up to the time at which I specify my Schrodinger wave function, and I evaluate it with the boundary conditions on the fields that they take exactly the same value as the argument of their functional there, right? It's a very natural definition of the wave function, and it's actually would correspond to if you write down quantum mechanics in a path integral formulas. So that's what you would naturally call the Schrodinger wave function. Okay, so in this picture it's really clear. So I told you exactly how to construct this state, right? All we have to do is to evaluate this path integral. So what we want to do, we want to actually go backwards, and going backwards in a path integral is slightly more complicated. So here, this is the relation from the operator, and we go back to the state. And so now, what we want to do, we want to see how in this path integral formulas, how do we go from this state? So, all right. Good. So, so what does the path integral describe, right? So the path integral with the slide, when I slice it, right? So for example, here, instead of integrating over the whole z plane, right? I just integrated over a unit disk, right? So the way how you have to think of this is that if there are some non-trivial conditions that I impose on my fields at minus infinity in time or at the origin in the z plane, then this wave functional describes the propagation of the initial state, right, to a final state over from t equals minus infinity to t equals 0, right? So this the path integral, so the path integral above so it describes the propagation of state initial at sigma 2 equals minus infinity to a final state. Sigma 2 equals to 0. Okay. The reason I'm saying there is 0 here is because if you follow the conformal map, absolute value of that equals to 1. That corresponds to sigma 2 equals to 0. Because sigma 2 is log of absolute value of that, right? Right. So to be more precise, what I mean here, I also have, so I provided the boundary conditions for the field kind of there at t equal to 0. But strictly speaking, I also have to specify that there is those. I have to prescribe the appropriate boundary condition at sigma 2 equals to minus infinity, right? So I integrate over particular particular configuration of fields which satisfy some initial boundary condition, and there is a final field configuration, right? And I propagate it from -infinity to 0. Okay, so is that clear so far? Okay, good. So now, what I want to do, I want to make this picture slightly more complicated, right? So, what I can do, right? So I want to integrate, I want to propagate a Schrodinger wave function, not from the initial state, but from some intermediate state. So this inner radius r, the outer radius is 1. So here, the time tau 2 equals log r, right? And so here, again, tau, so sigma 2 equals to 1. Yes.
Sorry, that's just a general question. How does this relate back to the expectation value of the operator A? Like what we were talking about when we initially.
Right. So when we talk about the expectation value, right? So then what we do, we integrate over all possible field configuration. So we prescribe field configuration. We do not. That's what they meant by cut the path integral open, right? So I cut the path integral at a specific time. So if I would continue and evaluate up to plus infinity with a set and prescribed boundary conditions there, then it would be a matrix element. Then this path integral will be a matrix element of the operator A0 between initial and the final state. Right? So what I do here is that think of it that there is an initial state, and there is this operator A that has an initial state, and I propagate the combination up to certain time. Okay. And I ask the question, what is the wave function of the states that I will get? And so that wave function is described as this person. Okay. So if you wish that if I push this up to infinity, the wave functions that I will get will be just for the final state. So if I just compute the, so I'm thinking that I'm projecting it on a specific final state. And then this guy will become just a simple matrix element, the initial final. Okay, good. So here there is a Schrodinger wave function corresponding to the state here, right? And so that's a function of phi sub b, right? And I denoted it. Sorry, it's a time t equals 0, right? So here I have a prime wave function, right? And so it also depends on phi prime, some prime values of the boundary state. And so what I'm going to do now, I'm just going to look at the specific path integral. So I compute a path integral. So I calculate over all values of phi, right? So I have e to the minus s. Right. So here my integral is over these panels, over this shaded region. So I don't integrate now up to the origin. I integrate. I have this e z, e to z. So I integrate absolute value of z larger than r, but less than 1. But when there is the action entering there. And so here what I do, I have psi prime. Psi prime. There is a wave function, psi prime. And then I integrate here. I have just an ordinary integral over all possible all possible phi sub b prime. Right? So what this class integral corresponds to, right? So I have a prime state. I have a prime state. It describes by Schrodinger wave function psi prime. And so what I'm doing, I'm evolving this state. So this state is defined at some time log r. And so I took this state and I evolved this state to, okay, so this is I'm going to put this as a, it's not the final state, right? Because usually we define final states at plus infinity, but let me still keep this subscript. So what I did, I evolved this prime state, right, to a state, to a final state at sigma 2 equals to 0. So this is our final state. I can put the initial prime state. And so, so in this language, I can ask what is the operator? What is the operator that performs this evolution, right? So we know that the states, that the Schrodinger wave functions are being evolved by a Hamiltonian of the system, right? And so, in other words, so this F equals to e to the minus Hamiltonian of the system delta sigma 2, the time interval over which I evolved it, and then this is my prime state, initial prime state that I started. So we can evaluate what this corresponds to. Well, in a conformal field theory, remember that up to central charge, this H is simply L naught plus L naught tilde. But actually, there is no central charge if I do evolution in the Z frame, right? So there is a central charge if I do the evolution in the omega frame. But here, since I define my states on the circles, right? So I have to evolve with the Hamiltonian in the Z plane, and the Hamiltonian in the Z plane is simply L naught plus L naught tilde. And so the interval delta sigma 2, right? So delta sigma 2 is just 0 minus log r. So this is minus log r. So I have to evolve over a range of minus log r. And so when I evaluate this path integral, what I'm doing here is my final state is going to be equal to e to the L naught plus L naught tilde log r initial state prime. Okay? So let me write down one more line here. So the final state is R to the power of L naught plus L naught tilde initial state prime. Okay? So this is a so we have two ways to describe this evolution. So the one way is to describe how the evolution occurs on the level of Schrodinger wave functions in the path integral representation, and this is a more familiar evolution of states. Right? So the important thing here is that I know how this I prime state is related to my final state. Right? So I know that I prime is R to the minus L naught tilde acting on my final state. Okay? So what this tells me that I know remember that what we do know, we know the state defined at time t equal to 0, right? A state defined at absolute value of z equals to 1. And what we want to do, we want to ask the question, what state it started with, so that upon path integral propagation, it ended with the state that we want. And so we see that here, if I have a wave function psi b of phi b, right? So there is a Schrodinger wave function here. So here, there was a different Schrodinger wave function. Okay, and so we know that to go from one wave function to another, I have this Hamiltonian evolution, right? So I have this operator r to the minus L naught tilde. So in other words, psi b prime must be equal to r minus L naught tilde active on psi b. Okay? And of course, the arguments must be the same. So here, yeah. So now this tells me that there is another way. How I can write down this final Schrodinger wave function, right? Psi b. So it's functional of phi b, right? So I can write it down. So I still have to integrate over phi b prime, right? And then there is a path integral over d phi, right? So this is such that phi as a boundary must be equal to phi boundary, right? So we evaluate over all passes, right? From that end up at a particular field configuration as we want in our Schrodinger wave function. Then here I have e to the minus s, right, the action that depends on the field. Right? And so here I integrate absolute value of z larger than r less than 1, right, in this action. So we integrate over this washer. And here I have to substitute the psi prime wave function up. And we just discussed with you that this is related to an original wave functional if I add backwards with it, with this Hamiltonian evolution operator. So what I can write here, r to the minus L naught, minus L naught tilde, and then here I have the same functional that I started with, but of course it must be phi b prime, right? And it's clear that the only thing I don't care what are the boundary conditions of the fields you start with on this inner circle. The only thing I care is that once I perform this path integral, I must end with a configuration of the field that I keep fixed. So that's why I have to integrate over all possible values of fields on the inner circle. Okay, so is this clear? Okay. So now notice that actually I have done not much. All I have done, I rerolled the identity. Right? You give me a Schrodinger wave functional here, and I can write it down as a path integral of this type, and it doesn't involve anything except the knowledge of this wave functional that you supplied to me, right? The only other things that I need to know is exactly what CFT you are talking about, because that CFT tells me with what Hamiltonian do I have to evolve it back, right? So this identity is true for any R, right? So I can put this in a circle at any distance. But what I can do now, well, I can write this down now as an integral of d phi. Right? I still have to keep phi b. Right? So this is a functional, wave functionals. Then here I have e to the minus s of phi, and now here I integrate over the whole inner. So notice that what I did, I took a limit when r So what we're doing, we're looking at the limit when r goes to 0. So I took a limit here. That's very simple. All I have to do is just to extend the integral in this action to the interior of the unit circle. But here I have limit r goes to 0 of r to the minus L0 tilde psi d of phi d phi. And of course, I have to integrate over d phi d phi. Okay. So of course, in the limit, as r equals to 0, that will define something that is localized at r equals to 0. So what we obtain, we will obtain precisely this operator that we're looking at. So now you can see that we can go, even from a path integral language perspective, we can go both ways. We can go from the operator to a Schrodinger wave function by computing that path integral, or we can go backwards. Okay. In the latter case, we have to evaluate this stuff. And that guy will give us the good. So now this is a little bit. I'm sure that most of you haven't seen this discussion before. So the Schrodinger wave functional representation. Did you see this before? So what we're going to do now, we're going to actually do one example very explicit. So we're going to use our X. We're going to use our XCFT, and we're going to compute the Schrodinger wave function. We're going to see what exactly that is. Okay. So we're going to look at the example of 3x CFT. And so what I'm going to do, I'm just going to look at a single x here, right? So I'm not going to look at maybe it doesn't really matter. So note that I have to specify a boundary condition for my field at z equals 1. And at z equals 1, there is only angular dependence. So I can say that x boundary, right? So this is the analog of what we call phi boundary, right? So it will depend only on the angle, on theta. And I'm just going to write it down in a Fourier coefficient expression. It's going to be a sum from minus infinity to plus infinity. That's n to the I and sigma. And so we impose a reality condition on our fields, which means that x minus n must be equal to x and stuff. Okay? So now you can think of that whenever I'm talking about this boundary functional psi boundary, right? So what I'm talking about, I'm simply talking about an infinite dimension function, right? So it's going to be psi boundary, and it will depend on this Fourier coefficient x of x. Okay. So once I tell you what we're going to do now, we're going to compute exactly. So this corresponds to some operator, right? So we're going to compute for some specific operators what this Schrodinger wave functional is. Okay? So any questions so far? So what we what we discussed earlier today is that there is a relation between operators and states. And so the simplest operator, the simplest example of this relation is that when we look at a vacuum, right? So this vacuum correspond to an identity operator. And so we argue very generally that that's an identity operator in this X CFT. And so now what we want to do, we want to see what is the ground state wave function. So in other words, once we compute sign 1 corresponding to an identity, so it's going to be an infinite dimensional function of these coefficients x of n. And so this is going to be a ground state wave function is going to be a Schrodinger wave function. Remember, in quantum mechanics, Schrodinger wave function depends on time, and so this is a ground state wave function at sigma 2 equals to 0. Okay, so we're describing how does our wave function look. If you know harmonic oscillator and the string theory, at least this three conformal field theory is a bunch of harmonic oscillators. So you might expect that the wave function we get here must be similar to the wave function for the ground state of a bunch of harmonic oscillators. Okay? And that's what we're going to compute right now. So by definition, now all I have to do, I just have to carefully file all this general discussion we did before. So by definition, so this psi1 is going to be an integral over dxi, right? So I have to, I don't know what I'm saying. So this is an integral over all possible values of field x, right? With a prescribed boundary condition. So this coefficients x sub n, okay? And I have to evaluate Hess integral minus 2 pi alpha prime. So here I have d2z del x of s, right? So this is our e to the minus s. And then remember that I need to insert the operator a. But in this case, our operator a is very simple. It's just an identity. Because we are asking the wave function corresponding to the identity operator. And we have reasons to expect that that should be a wave function for the ground state. Okay? So let's go ahead and compute this Hess integral, right? So this field S depends on that bar, right? And so what I can do, so it's a quantum field, right? So when I evaluate Hess integral, I have to integrate over all possible fields with a prescribed boundary condition. So what I can do, I can write this down as x classical as a function of z bar plus x prime as a function of z bar. Okay? So what I mean by that, so I separated, if you wish, a classical plot, and I separated a quantum plot. At this stage, classical and quantum separation are a little bit funny because in this Hess integral, I just have the field is just ordinary function. So it's the only thing, the reason I did this separation is because the classical adds classical at z equals to 1. I will say that the classical part of my field satisfies the correct boundary condition, right? So it's xb as a function of sigma, which is this infinite sum, right? From minus infinity to plus infinity. And then I have xn e to the I and sigma. And moreover, what I'm going to do, usually, the classical part, so when you evaluate the Hess integral, so there is a classical trajectory. Classical trajectory always satisfies the equation of motion. So we're going to do exactly the same thing here. We're going to require that x classical satisfies the equation of motion. And x prime are the fluctuations, right? So this is those are fluctuations. And so the fluctuations are pretty much arbitrary non-singular functions that we have to integrate inside the case. And because we already satisfied the boundary condition with the classical part, the fluctuation part, x prime of that z bar, when I evaluate it on a unit circle, must be 0. Okay? The important thing is not whether it's 0 or not 0. What is important is that it doesn't depend on xn. Okay, so this is a crucial part, right? Neither So in the path integral, we integrate over any configuration, right, which are non-singular. And the only dependence on the boundary condition would come only from the boundary condition. And we specifically did the separation in such a way that our fluctuating part does not depend on the boundary condition. So what this tells me is that I can do this change of variables in the path integral that defines the ground state wave function. I'm just going to write it down as so there will be a factor e to the minus 1 over 2 pi alpha prime and integral d to z, and I have to integrate over the interior of the disk. And so here I have del x classical, right? Del bar of x classical. So this is just going to be a constant. It's a fixed, if you wish, classical trajectory. So I can take it out of the path integral, and then I will be left with a path integral over all configurations of the prime field, right? And then I have with the boundary condition that they must be 0, right? And so here I have e to the minus s, okay? And in this s, well, e to the minus integral d to z del x prime del bar of x prime. Okay, so is it clear? So the cross terms will not be important because once I have the cross terms, well, you can check for yourself that they will just drop off. Okay, so so the point that I want to make now is that this complicated path integral that we would have to struggle to evaluate, not really struggle because it's still a Gaussian path integral, but the important point is that it doesn't depend, does not depend on xm, right? So xm are the arguments of our Schrodinger wave function. So this provides just some normalization constant. So what we know that psi1 that depends on xm is going to be some constant e to the minus 1 pi alpha prime and integral less than 1 d to z, and then have del x classical and del 1 of x classical. Okay? And so then what we have to do is clear, right? We just have to evaluate this exponent. And the first step in evaluating that exponent, I have to tell you, we have to solve pretty much the wave equation for the x classical, right, on a disk with a specified boundary condition. So what do we know? We have 5 minutes, and I should be able to at least finish it in this. And we will not let anybody in. So, right. Okay, so first of all, we know that that del x classical is just holomorphic piece, right? So it's del x classical according to the equations of function, and del bar of x classical is just del bar of x classical as a function of their bar. One is a holomorphic piece, the other one is purely anti-holomorphic piece. And so I'm just gonna write down the solution for you, and you can check that that's indeed the case. So I'm just gonna say that x classical, and of course x classical must be a single value. So the solution to this boundary partial differential equation is unique. Okay. But instead of trying to solve it, I'm just going to write down the solution, and we'll all agree that that's indeed the solution. So it depends, x classical must depend on that and that bar. So there will be a zero mode piece, x naught, and then there is an infinite sum, n equal 1 to infinity. Right? I'm looking for a solution which is a smooth function, so it's a classical trajectory, no singularities. That's why there is only a Taylor series extension, xn plus z bar x minus. Okay? So first of all, you can immediately see that when you act with del or del bar, you will get either holomorphic or anti-holomorphic. So it must satisfy equation of motion. That quickly answers the question. Second, you can see that it also satisfies the boundary condition, because at the boundary, right? So at the boundary, what I have the z equals e to the I theta, and so this sum goes into sum n equal 1 to infinity. Then I have x to the n e to the I n theta plus x to the minus n e to the minus n theta, right? So which is exactly the boundary condition that we started with. And then there is this x naught, and so this x naught is just exactly the x naught phi in the boundary condition, right? This is n equals 0 piece. So is this clear? So we all agree that that's a solution. It must be a solution because the equation of motion simply tells us that del x must be holomorphic, del by x must be anti-holomorphic. So I showed you this is a smooth solution, satisfies the right boundary condition. Okay? So once we know what the solution is, we can now go ahead and evaluate this experiment. Well, we can just compute the integral, right? So the integral is, I have to evaluate. I have to evaluate 1 over 2 pi alpha prime d to z absolute power of z less than 1. Del x classical, del bar x classical, right? So I substitute this expression up here into the formula here, and so at the end of the day, I will get an integral, right? So the routine becomes 1 over 2 pi alpha prime. So there will be a double sum, right? Because I have two fields. So one is the summation with respect to n, the other one was summation with respect to m to infinity. And so here I have m times n. Those will come because I have to act with derivative. And then I have xn, x to the minus n. And then I have an integral absolute value of z less than 1. D to z, and then here is z m minus 1, z bar m minus 1. Okay, so this is a really trivial arithmetic. I just substituted the expansion. Okay, so computing this integral is also very trivial, right? Because I can go this integral doesn't look very nice. It has holomorphic and anti-holomorphic part. But I don't have to care. I can just evaluate this as simply the integral dr times r, where r goes from 0 to 1, and the integral with respect to theta, where theta goes from 0 to pi. I can think of this as simply a polar integral, right? And so that is simply r times e to the I theta, and z bar is r e to the minus I theta. So I just plug it in and do my undergraduate calculus. And so what you will find out is that this integral, I'm not going to do here for various reasons. One of them is there is no time. What you will find out is that the answer is 2 pi divided by m. Okay, and then there is a conical delta symbol. Okay, so the integral vanishes unless m equals minus n. Actually, because this is pi here, so this is m comma n. So having said that, we now have a wave function. We now have a wave function corresponding to a ground state. Okay? So this psi1 of xn equals to, well, up to a constant, so I'm just going to write down is proportional to the exponential x, right? And then here I have, so the integral is 2 pi over m, so m will cancel, 2 pi will cancel, so I will have minus 1 over alpha prime, and then I have sum m equal 1 to infinity. So notice that m must be, yeah, so actually I am right here, sorry guys. So it's, well, you can check it yourself, whether it's m plus m, anyway. So there will be a minus sign here, and then I will have here m x m x to the minus m. Okay, so this is indeed what you expect for the wave function for the ground state of a simple harmonic oscillator. Okay, so are there any questions? Okay. You can see that this is something very straightforward. There is a definition, what we mean by Schrodinger wave function, and we just went into some small pains in order to evaluate. What I want to do one last step, and now we can be kicked out any minute, but it's going to be 3 minutes, but that will allow me. We're not done with the CFT. There is a little bit left, but at least that's a good last point. So remember that one of the property, if the ground state wave function for the harmonic oscillator is being annihilated by annihilation operators, right? So this is a fact that must be familiar for you from just quantum mechanics. So what we expect that when we act with alpha n on psi 1, then we should get a 0. So alpha n we want to write down as a differential operator, much like we would have done for the harmonic oscillator, and we want to check that this as a differential operator, when it acts on a ground state wave function, it must annihilate. So how do we figure out, how do we write down it as a differential operator in terms, so remember in the case of the simple harmonic oscillator, this was x, some constant del x, right? So this was a combination, these annihilation and creation operators were a combination of x and del over del x, right? Del over del x. So those were x plus p and x minus p combinations. So the analog of x now corresponds to these Fourier coefficients x sub n. So what you can check that if we define alpha n minus I n over 2 alpha prime is 1 x to the minus n I alpha prime over 2 del over del xn. So sake of this is that now I have an infinite set of simple harmonic oscillators indexed by n, and so correspondingly I have an infinite set of alpha n, and so I have this, and correspondingly for Wilder ones minus I n over 2 alpha prime 1/2. So here I have n alpha prime over 2. So you can check that if I represent it as a differential operators on a configuration space of my wave functional, right? So those are differential operators that act on something that depends on xn. They satisfy the algebra that we derived before. You can usually check that when this definition is true, then alpha n equals to m delta n minus n. Okay? again, this is exactly, you would have to do exactly the same steps as you do for a simple harmonic oscillator. So if it's not clear, I'm gonna do this explicitly next time. But the important thing now is that you have a specific representation for the alpha n, and I can assume that n is positive. So what I can do, I can now evaluate alpha n at psi 1 of x dot n, right? Probably want to keep different indices. So there will be a differential operator acting on some exponential, and you can do this arithmetic, and you can see that indeed that equals to 0. So as expected, much like your intuition from the simple harmonic oscillator, the differential representation for the annihilation operator annihilates the ground state. So the same works here. All right, guys. So sorry for running over time a little bit. And please take a look again, and if there are questions, ask me. One last thing, homework. I'm going to tell you the problems now, but you will have at least 3 weeks, okay? So, because next, we're not going to have something for which you can do some computation for quite some time. So the homework assignment I want to do, so homework, so it's going to be 2.3. And 2.8, 2.8, and 2.13. Okay? So you can do all of them already. So this is just some problems on conformal field theory, and it will help you with understanding later. All right, guys, see you next week. Bye-bye.